So welcome to this session where I will explain you how you can use that class data sharing option of the JVM itself, how we can use that to speed up your Java application startup. And as you will see, that's a very neat feature because you can get some great performance improvements on startup and without the need to change your application, without the need to use specific libraries, to use specific frameworks. And as you all know, the fast startup of an application is a hot topic today, so that's a very nice feature then if you know how to use it. So what happens when you load a class, when the system loads a class in the JVM runtime? That class, that bytecode is loaded by one of the loaders. You have several of them on an application server. You can have even more of those class loaders. But they locate the bytecode for that class. And then some important steps are done before that bytecode can be used. There is the verification of the bytecode to see that there is no malicious tampering done with it, and also that the class is effectively correct for that version of the JVM. There are some preparation steps. There is the resolving step. So all those actions are required because otherwise the JVM cannot use your class. But that's the main reason why the JVM takes some time to start before the requests from a user can be handled. So instead of looking to alternatives like native compilation, we have a look at that class data sharing, and I'll explain you also with a demo how you can use it, and then you can see it in action. I'm Rudy de Busscher. I'm working for Payara as product manager, but also giving some presentations like this one. I'm involved in the microprofile specifications and the Jakarta ones, but that's not the topic for today. Today, as you know, I'll talk a bit about the JVM internals related to class. You don't need to be an expert to know how all those system works. I'm not an expert either, but with some basic concepts, what's happening, then you understand better what CDS is and why the JVM takes some time to load a class. But we also take a step back to ask ourselves, is that fast startup really important in all cases, or are there scenarios that it is important and other it's not? And then I'll tell you about the basics about that class data sharing and the demos, as I mentioned. So when the JVM sees the statement new my class, for instance, then several things happened, as I showed you on the first slide. The loading of the bytecode through one of the class loaders is most of the time not a real issue in terms of performance. If you have a very large class pod, as some runtimes have something like 70 or 100 different jars which they put on the class pod, it can take some time before the class is found, but in general it is never a real issue regarding the performance and regarding the startup. The second step, the verification, that's one of the things that takes more time. And the verification actually is needed because Java works with that two steps. You first have the compilation to bytecode, and then later on that bytecode is used by the runtime. But the time, in the time between the compilation and the usage of that bytecode, that can be huge. It can be sometimes minutes if you don't do it locally, but if you are using one of the libraries, one of the frameworks within your application, then the code then is compiled, is uploaded to Maven Central. It passes through your local nexus of your company, etc. So there is a huge time delay between the compilation and the usage of that code, and in that time, a lot of things can happen. You don't hear a lot of things that there are malicious changes to that bytecode, but it can happen, of course. That's also the reason why, for instance, Maven Central made it mandatory that you are using the secure protocol, that the SSL protocol, that you use HTTPS when you're downloading artifacts from Maven Central. But the verification does more than some general checks about manipulation of that bytecode. One of the things is that within the class, you have there the version which it is compiled to. You add those magic numbers, 52, 53, etc., that indicates the version of the bytecode which is in there. Because the bytecodes, they change, they evolve. For instance, now with JDK 17 and those record structures, they have added new bytecodes. So, and that's a fun thing to do. If you have something, if you have some half hour to spare, take a record class, or so that record construct, compile that to JDK 17, that class, and then change that magic number to match a JDK 11 class file. And then you try to start it up with the JVM on JDK 11. That verification steps will see then that, okay, the class file itself is JDK 11, but there is a bytecode which does not belong there. So you will get an error. That verification is also needed because the JVM today is no longer pure Java. There are other Java languages, JVM-like languages, Kotlin, Groovy, all those other languages. They also compile to Java bytecode. And of course, there is a specification which defines how a class file and the bytecode, how that should look like. But of course, the JVM needs to verify if that bytecode really is correct, because it's not only the Java compiler that creates bytecode. So that verification step is one of the possible reasons for that performance issue. But there is more that needs to be checked. That's what's called class file derivation in the specification. Because again, at compile time, you can compile against a class or an abstract. Let's call it an abstract class foo, which is in a certain version of your library. But at the runtime, you can have maybe a different version of that same library there, and that abstract class is changed to an interface. That kind of things will result in that incompatible class change error, because the JVM cannot handle that. And I know that you should avoid to have different versions in at compile time, at runtime, but there are always situations that there are small differences in versions, also because for instance, in the world where I'm living in, the Java enterprise world, there is a specification and an implementation, and there might be slightly different versions around. The next step, what is done by the JVM system, is what's called the preparation, which is more or less the variable initialization. And normally, that does not give you any issues. Setting a value to 0, initializing it with a constant string value or whatever, that is not the issue. If you, of course, create a static initialization block where you call a certain endpoint wherever in the world and expect some answer, etc., then, of course, that will also delay your class initialization. So don't do those things in a static initialization block. And the last step, the resolution, has to do with the invoke dynamic construct, and that's created partially for those JVM languages to have more dynamic constructs possible. It's also used with the lambdas and the streams implementations. Because there, at compile time, there is no check at all. It's only done at runtime. So there needs to be, of course, a very proper check to see if it's valid or not at that time. So from those 5 steps before the interpreter can use your code, there are 2, possible 3, with those symbolic references that can explain why the startup of your Java application takes a few seconds. So there are people try to find improvements already for years. I remember even that no verify option. I remember that even that 10, 15 years ago, people said, well, use the no verify option and everything goes faster. Well, that's true. But that's only that one single step that you exclude, that the verification step. But again, that can be quite dangerous. So I'm not going to say that you should use that in production, because that's a really dangerous thing to do. And other solution, and that's gets a lot of attention these days, is native compilation. So that instead of using that class loading, etc., that you instead of compiling to bytecode, you compile to native code of your operating system. Then you exclude all those steps. You avoid all those performance issues. But native compilation today is still slow, much slower than just normal Java compilation. I have no doubt that it will change in the future, but I don't see any developer today in his development environment compile to native code and then see if it works or not. So then you get the difference between what you're running in production with native compiled code and locally you're just using bytecode. And to be honest, I had some fairly bad experiences, not with native compilation, but with other frameworks some 10 years ago, where you also had the difference that you have a dev mode locally doing something else than a production mode in production, where you see all kinds of differences and you have no clue where you have to find, because it is something completely different. Another, and that's maybe a more important factor, is that your native compiled code has what's called a lower peak performance. Native compilation has no ID. Well, there are some possibilities now with some execution profiles, etc. But normally native compilation has no idea what your code, how your code will be used at runtime. Can it be optimized, yes or no, or how can it be optimized? For those who followed the talk of Simon, Simon narrated this morning about also AOT and JIT compilation, there about it, preemptive speculation, etc. He showed there a nice example that native compilation will always perform all the checks because it has no clue if that value will be greater than 9 in this example. So the JIT compiler is so optimized during the last 25 years that once it is warmed up, when it is seeing what is happening, that it can create for those hotspots, for those things which are really used a lot and take some time, that it can generate very efficient native code, better, faster and better code than the native compilation can do. You also have issues with native compilation with reflection. You have to specify where it can happen, what are the outcomes, etc. Because it needs to know that at compile time. You have also those issues with the debug options. Okay, you're not going to use it in development, but that's another issue that you have. You have the problems with Java agents. You cannot change the code on the fly by a Java agent for monitoring purposes, etc. So if you ask me, native compilation is not a solution for that slow startup that we have today. But the third option, and that's also there within the JVM, it's already there for around 5 to 7 years, is what's called class data sharing, CDS. And the good thing is about CDS is that it just takes your application as is, it keeps it as Java, but it allows you to get the startup and the loading of the classes to be done very fast. But if you ask me, we need to take a step back because everyone is talking about a fast startup, and in microservices it is probably more important indeed than in other environments, but is it really important for your case? Is it really important that it starts up in half a second or starts up in 5 seconds? That's not much difference. Okay, in absolute terms, it's about it's about 10 times slower. But is it really worth of all the work that we do for those 4.5 seconds? And then I'm not talking about that cold startup problem with serverless function, because for me, if you say I'm going to use a serverless function, that means that I don't need to have it running all the time, so I'm not using it a lot, because I only use it occasionally, so I don't care if it takes half a second or 4 seconds to start it up, because otherwise, if that's the issue, then my application should be running all the time. But okay, I have here an example. You have created an online application to sell tickets for events and concerts, and of course, if you announce that there will be a concert of a popular rock band, for instance, you will probably see a higher raise in those requests as seen by that orange peak at the end. Your system can be optimized for a certain amount of requests. That's the blue line. If it goes over it, then you need to start up an additional instance, because otherwise people will see the spinning cursor or get even error messages because they are rejected because the site is overloaded. And then, of course, I can imagine that you need to start up as fast as possible, and then half a second or 5 seconds can maybe make a difference. You also can do, of course, start it up a little bit earlier, but then if you have only that bump just before the high peak, then you might have started up an instance which was not needed. Bottom line is, I don't believe that every system should start up fastly, should start up very fast, there should be some real use case for it. But okay, we have identified that we need to improve the startup. What can we and how can we do it with class data sharing? And the name is very confusing, because when I first read about CDS about 2 years ago, it was class data sharing. Is that sharing of data between classes like static variables? But anyway, you will see later on why it is called sharing of class data. I mentioned there the loading, the verification, all those, and the derive step, that it takes some time. But actually, if we could do that upfront, not at the time that the JVM starts, then we can get much faster response, of course. So the idea was, what if we put all the class data information in the format that the JVM needs, that it is verified and that it knows that, for instance, in that arrive phase, there is also the check if you call a method on a certain class with 2 parameters, string and int, that they are actually in there, in that class, etc. If all that information is stored in what's called a memory map to read-only file, and that file is, that's why it's called a memory map file. That file is mapped in directly into the memory space of the JVM. Then the loading of the class is much faster, because there is no loading at all anymore. All the information is already there in that memory map file, and since it is read-only, we can assume that no one has tampered with it. You will see later on that it is even read-only for every user on your machine. So actually, you cannot change it unless someone with root access changes the permissions, which of course you should not do then. So CDS is creating, and there are different formats. In the beginning, it goes even back to JDK 8. There you had a simple version. Later on, you had the application CDS. Later on, you had the dynamic CDS. But all of those versions, they create just that memory mapped read-only file that is used immediately at startup of your application and eliminates the entire class loading, verification, and derive steps. The sharing comes from the fact that that memory map file can be used for multiple processes on the same machine. So you can share that single file with 2 JVMs on the same machine, of course. That's where that data sharing name comes from. And is it then a real, for instance, you will see later on the actual percentage, but if you have an X amount of percentage faster startup, is it then important? If you check out the typical hello world example, public static void main method, system out print line hello world, that uses around 437 classes in the JVM. That's also one of the nice things that you can see with CDS, how much classes are my application are using and which classes. So more on that in a minute. Starting up that hello world, making that hello world faster, that is of course then with X%, but that will be in the time scales of milliseconds, which is not worth of it, of course. Payara Micro, which is a Jakarta EE web profile implementation, uses around 15,000 classes. If you eliminate the class loading for all those classes with that X amount percentage, then that can be a significant difference that you can see, that you can measure in the time that it requires to start it up. So let us see how much time it takes and how much faster we can do it. I'm going to use still JDK 11, but I'll also mention JDK 17. And I'm using a OpenJDK version, but also OpenJ9, because OpenJ9 has a very interesting implementation of CDS in this regard. So let's double check if it's the correct version. Yes, it is JDK 11. It is actually the Zulu 11 that I'm running here now. So let's make a reference call. Let's see how much time it takes to start up Payara Micro with a simple application, without any tricks, just as you normally do if you don't know anything about CDS. The nice thing is that when it started, it gives you the time that it took to start it up, and it is now 8.6 seconds, as you can see on the screen. Remember that value, because later on we will see how much faster we can make it instead of that 8.6 seconds. The first thing that we need to do with CDS is, and that's related to Payara Micro, if you run this command, within that Payara Micro jar file, that's an executable jar file, but actually it contains all the different jar files in it. It is expanded in the temporary folder, and then all those jar are added dynamically to the class path. You can imagine that all that hocus pocus of dynamic adding things to the class path is not a friend of CDS. So that's something what is not going to work. So that's the reason why we have then what's called an output launcher. I have to find the correct command here. So this command creates in that micro root directory what it does normally in that temporary folder, so in lib and runtime, all those jars are there, but there is also now a new jar file called launch micro, which is just a single class that starts it up, the entire system, but in the meta-inf directory, the meta-inf file of that jar file, the class path is really hard-coded, saying that these are the files, these are the jar files in the lib and runtime. That means class path is 100% determined, which is required for CDS. Now, with OpenJDK 11, you need to specify which Java classes needs to be put in that memory archive file. You can do that by just creating a file and putting all the fully qualified class names. As I mentioned, 15,000, you're not going to do that by hand. How you would even find out which classes. So there is luckily an option. It's an option that you can say when you start up the Java that says dump loaded classes list. And that generates then the class loader generates then that file for you. And we have here that within Payara Micro, this parameter, that option warm-up, that actually says that this is a warm-up run, so that when the entire system is ready, so Payara Micro is started, the application is scanned, we know everything, then at that point, we just shut down the instance again. But due to that dumped loaded class list file, we have now here that file with those 15,000 classes, which contains the Payara Micro classes, which contain the JVM classes and contains your own application classes, because the application is scanned at startup to know everything. For instance, for CDI, there is an entire scanning. So that means that we know everything. And this classes list then can be used to create that memory mapped archive file. That's the next step. With the option -x share dump, you can say, based on that classes list, create me that archive file called payara.jsa. I saw that many users are, in the demos and in the documentation, there is a .jsa file, so I'm just using that. And as class path, I specify there that launch microjar file, that output launcher that we have. This does not start up your application, and this is different with OpenJ9 and JDK 17, and is actually a long and tedious process which you can compare with native compilation. So it goes each line of that file, loads the class, do all the verification and the derivation, and you also see that some classes cannot be found because these are dynamic proxies which were generated on the fly by my JVM, by Payara Micro or your application at the time you started up. But that's not an issue, because it is still pure Java, pure JVM that we are going to use with CDS. So if it's not found, then later on at runtime, then we can just use that or generate that file. So that's not an issue. I'm going to stop it because it takes some time. And I did run the example before, and I have here that JSA file already of a previous run. You see that it's purely read-only, so no one can change it. And the size is about 155 megabytes, which is a lot. But remember, that's the entire JVM, entire Payara Micro, and your application. In OpenJ9, and especially in JDK 17, by default, the JVM is left out of that because the JVM itself has already such a archive file, and there with JDK 17 you can use multiple archive files to combine it in memory. But now that we have that archive file, we can start up Payara Micro with our application, specifying that we have that that we are using that archive file there, Payara demo.jsa, and we specify again that output launcher, that jar file, because we still need to point to the class path in case there are some classes missing, and I'm coming later to a list of which are not put in there by default. It was 8.6, remember? Now you will see that there is a significant performance improvement on 6.7. My machine is doing now a few other things also with sharing here. We have done some more controlled experiments, but from 8.6 to 6.7, that's almost 2 seconds. 2 seconds out of 8, so that's 25%. It's the same jar file, same Payara Micro version. I did not change anything, the same WAR file. The only thing that I did was some tricks with class loading. But OpenJ9 has some other interesting feature. So let's switch to OpenJ9 here. Double check if it's correct. So you see it's OpenJ9, and I have here also ahead of time enabled for OpenJ9. So immediately, as soon as possible that OpenJ9 sees an opportunity to generate native code, he is generating native code. I'm not going to do the version without CDS because that's more or less the same. You see the statistics later on. I'm not going to create the output launcher, so I'm going immediately to create that archive file. You need to specify it a bit different because OpenJ9 had from the beginning the idea, why are we creating first a file with all the classes, then create that archive file, because at runtime, all that information is available within the JVM. So why don't we have just an option that when the JVM exits, that every piece of information that we can use about those classes, which are in memory, are just dumped to that archive file. So we have done here just the -x share classes, which define the name of that archive, the directory. We specify a size, 300 megabytes, which is way much too high, but you will see later on how you can find out what's in that archive file and that you can maybe optimize the size. Again, that output launcher, that warm up so that it stops, that Payara Micro stops when everything is ready. Again, it started up. This is a normal startup. It immediately shuts down due to that warm up, but that info then is written to the archive file due to that OpenJ9 functionality. If we print out then the contents, because you can have a look at the contents of that, let's first have a look at the file. Because there is another interesting thing here. You see the file here, 300 megabytes, so that's around 314 million bytes, but you see that the file is not read-only, but you can also write to it, because the idea is that this is an iterative process. You use that archive file, and at runtime, more information is learned by the JIT compiler, more AOT, ahead of native code is generated, and at the time it stops, that all that information is dumped again to that file. So it is an iterative, ever-improving solution. So what is in there, in that file, then let's have a look. You have an option for that. Here with that print stats, so you give the option print stats together with that cache dir and the file name. And then you see that it's only 27% full, so it's definitely not containing my entire JVM. So it contains only Payara Micro and my application. But as I said, since I am using immediately native compilation, there is already a large amount of native code in this cache. So by using this memory mapped file, not only class data is loaded, but actually the native compiled code. Can you see the difference? Yes and no. Sometimes it depends on the case. So if we run it here, and in our tests, we could not make clearly the difference between if there is the ahead of time compilation, yes or no. So let me start it up. This is the correct one. So share classes. Where is my memory map file, my archive file, and then just my path, just as with the version of OpenJDK. And then it starts up, and you will see. And most of the time, my timings are here bad. You see, now it's 7.9, so that's not that much improvement. But with the controlled environment, it was better. Combine this improvement of CDS with the rather large improvements they have done on the garbage collections in JDK 17. I have tested that with for another talk, that you can have improvements in performance about 20% by just using the same application on JDK 17 instead of JDK 11. So combining CDS with that improved garbage collection algorithms, then in JDK 17 you can have a much faster system without changing a single line of code. So this is just for reference. The main options: the dump load class list, the archive file, share dump to create the archive file, on to use it, that archive classes at exit, which is used at JDK 17. So there again, you don't need that class, that file with that classes list. And OpenJ9 uses that xshare classes. Now, these are the results of the more controlled test that we done. And then you see that you can go from a normal starter from 8.2 seconds to something to 5.2, which is significant. Same for OpenJ9, and there you see that it was a bit faster, but not really spectacular. But we also found and we confirmed that the claim of OpenJ9 saying that they are much more memory efficient is also true. You see, only around 45 megabytes of heap used instead of the 50 with OpenJDK. So that's around 10%, which is, if you ask me, a rather good thing. If you do some maths, you come around 35% improvement in startup of the application with CDS. You see there are several steps, especially with OpenJDK 11. So, but if you are using a Docker file, then you can use, of course, a multi-stage Docker file, and then you can do that all in one thing, in one go. You don't need to type everything in. You can even decide, for instance, to create a shared archive file inside that image, and then as a layer, so that you put your JVM and your Payara Micro, for instance, in that archive file, but not your application. Then your application is not making use of it, but all the rest is using it, is making use of it, and you still have a very efficient Docker image where only the application layer needs to be changed with your application. Or you can define it outside if you say my image needs to be small, because again, the size of your image grows, of course, if you put that memory mapped archive file in the Docker image. So if you are using Postman, it's not possible with the standard Docker clients, but with Postman build, you can immediately create that archive file on a volume. few pitfalls mentioned already. The class path must be identical. So even if I create two output launchers for Payara Micro, and the archive file created with one launcher is not usable with the other one. So he keeps a lot of information from what is the class path, where was my application located. So that class path is very important. Also mentioned dynamic proxies. Older 1.5 and older classes cannot be used. So you get just a message that it will be removed from the archive file, but since you still specify the class path at runtime, it is just loaded, but through the classic way. It's no surprise that that archive file is JVM version and OS dependent. I don't think that's any surprise. So don't try to put an archive file from Windows on Linux or vice versa, etc. And if you might have issues that you need to investigate, and we are using now this CDS also within our new product which is coming out, Payara Cloud. So we did not see anything for the last two years. But if you might have issues, you can use the -xlog load plus class to see what's happening and how all the loading is done, etc. Thank you for attending my session. If there are any questions, please feel free to call to ask them or find me after the session.